In this video, we're going to address weak acid-base solutions, buffers. So remember, our weak acids are things like acetic acid, where they are in equilibrium with their products. So an acid gives away H+, so we have our acid over here on the left. Base, AC-, can consume H+. So if you do the reverse reaction, you have to meet up with an H+ and react with it. So the AC- will consume that H+ to go back to the left. So it is a base. Weak acids and bases are molecules that, while in solution, reach equilibrium. They don't fully give away H+, they don't fully consume it. So HCl was a strong acid because it completely gave away all of its H+. And sodium hydroxide is a strong base because it always consumes all the H+ it can find. Acetate, AC-, will react with H+ to form acetic acid, HAC, but it will reach equilibrium. And the acid breaking apart will also reach equilibrium. Well, if we have equilibrium, remember that your Q is equal to your products over your reactants. Since acid and base chemistry is so phenomenally fast, we never really find a Q value. It reaches equilibrium before we can do anything. So realistically, whatever the amounts are have always adjusted until you've reached equilibrium. So they're always at equilibrium. So KEQ is the same idea. It's still my products over my reactants. Just the amounts have changed until the rates forward and backward were equal. If you are working with a weak acid, then we use the symbol Ka. It is KEQ. It is the equilibrium constant. It is just to tell you you are working with a weak acid. For acetic acid, the Ka is 1.8 times 10 to the minus 5 for acetic acid. Knowing this, though, since it is in equilibrium with H+ and AC-, we can write its equilibrium expression. We can say that, hey, the Ka must equal the product's concentration, H+, AC-, all over the acid, HAC. Every weak acid is going to look like this. You're going to have the H+ and the base on top, the H or the acid on the bottom. Doesn't matter if it's ammonium, doesn't matter if it's hydrofluoric acid, doesn't matter if it's carbonic acid, citric acid, anything else. They all have this same setup. H+ and base on top, acid on bottom. Why this is useful then is if we know 3 of these 4 unknowns, we can solve the rest, or the other one. So if you know that you add a solution that is 0.14 molar HAC and is also 0 to 5 molar AC-. Right, and you can obtain the base as a sodium salt. That's the most common way is you use sodium acetate because it's the same. If we think of acetic acid, it looks like carbon with 3 hydrogens. Carbon, double bond oxygen to an oxygen to a hydrogen. You can react this and you can make sodium acetate where you've basically swapped the H out for sodium. But when you add this to solution, it means you just get acetate. So it's easy enough to obtain just the base from one source and just the acid from another source and mix them. If we do, Well, we said the Ka was 1.8 times 10 to the minus 5. That must equal some H plus concentration times our base concentration, so 0.025, divided by our acid concentration, 0.14. Rearrange this to get H plus on its own. It's going to be 1.8 times 10 to the minus 5 times 0.14 divided by 0.025. So rearrange the things from left to right. Give me a sec. 0.14 divided by 0.025 times, in parentheses, 1.8 times 10 to the negative 5. This is 0.000101. That is our molarity of H+. So we didn't need a lot of H+ in order to make the top very small, because, well, if we think about it, our Ka is very small. We don't want very much on top when we do our division. So I needed a very small amount of H+, so that when I multiplied it, I got a very small value for Ka. We can always calculate the pH of an H+ concentration, which is how most buffer questions will go. You will be asked to find the pH. So pH is negative log of the H+. So in our case, negative log of 0.000101, I get 3.997 as our pH with 2 sig figs. And what we haven't talked about yet, when you have a log, the number in front of the decimal technically doesn't count for sig figs. We'll address that more in a future video. But so this would be 4.0. 4.00 is what it would round to. So this is a fairly acidic solution, and we have significantly more acid than we have base. Let's use those same values. 0.14 acid, except this time we're going to use a just different weak acid. So we're going to 0.14 molar NH4 plus and 0.025 molar NH3. So we use the same concentrations of acid and base, and we're going to find the pH. I will tell you the Ka for ammonium is 5.6 times 10 to the minus 10. So the only difference here is a much smaller Ka. Well, as a result, when I set up my equation, 5.8 times 10 to the minus 10 is going to equal my H plus, my base, 0.025, which referenced earlier, we're setting it up the same, just plugging in our new values. Our acid's still 0.14. The difference this time is I need a much more tiny Ka. Previously it was 10 to the minus 5. This is 10 to the minus 10, 100,000 times smaller. I need my top to be 100,000 times smaller. Well, the acid and base are the same, so the only thing I get to adjust is my H+. It has to be smaller to make up for that. This is what we're going to find when we solve for our H+ here. So 5.8 times 10 to the minus 10 times 0.14 divided by 0.025. I get 3.25 times 10 to the minus 9. Previously, we had 1.01 times 10 to the minus 4. So 5 powers again. For 5 powers smaller H+ to make up for the 5 powers different in our Kas. If I try to find the pH of that, the negative log 3.25 times 10 to the minus 9. So 8.49. So for the exact same mixtures of weak acid and weak base in terms of concentration, we get wildly different pHs. This is because acetic acid is good at being an acid, like it's in the name. But ammonium, we think of as a cation. It doesn't call itself an acid. Ammonium is not very good at releasing H+. And so it favors holding on to it, and so it tends to consume the H+. All right, let's give a shot. Try to calculate the following. I've got 0.0025 molar HAC and 0.0175 molar AC minus. And remember, my Ka is 1.8 times 10 to the minus 5. Find that pH. Go ahead and pause here, take a minute, and then come on back. All right, so set up our equilibrium expression. Our Ka will equal our H+, our base, over our acid. Well, our base was 0.0175. Our acid is 0.0025. So our H+ concentration, 1.8 times 10 to the minus 5, times our acid, 0.0025, divided by our base, 0.0175. So 1.8 times 10 to the negative 5 times 0.0025 divided by 0.0175. 2.57 times 10 to the minus 6 is our H+. And so the negative log of that value, our pH, is going to equal 5.59. In this case, I had far more base than I had acid, and 5.6 versus our first problem, where I had a lot more acid than I had base, and our pH was 4. So by swapping to having a greater concentration of base, I have a higher pH. And remember that higher pHs are more basic. So the more base comparatively you have in your solution, the more basic you will be. The more acid you have in your solution, the more acidic you will be. But which weak acid and base you use can start you in very different realms. Our ammonium is generally way up in the basic area to begin with, and our acetic acid is down in the acidic area to begin with, and can just move back and forth within its realm a little. Well, let's compare two things real quick. Let's do 0.1 for the acid and 0.05 for the base. So we'll speed this one along, find the pH real quick. That'll be 1.8 times 10 to the minus 5. It's going to equal our H+, 0.05 over 0.10. H+ in that case, 1.8 times 10 to the minus 5 times 0.1 divided by 0.05. 3.6 times 10 to the minus 5, negative log of that. pH is 4.44. Try this one. Let's dilute the solution. I have 0.010 HAC, and I have 0.005 AC minus. So I have 1/10 as much of both of them. Go ahead and pause here, take a second, find that pH. Alright, if you gave it a shot, well, we'd plug it in the same. 1.8 times 10 to the minus 5 equals H plus. So this time 0.005, much over 0.010. So we have 1/10 as much stuff, but remember, we're just multiplying and dividing. And so effectively we always had twice as much acid as base. And so if you have 1 over 2 versus 10 over 20 versus 100 over 200, the ratios are still the same. It's 2 to 1. Since we're dividing, when we divide, that still is true. It's still a 2 to 1 ratio for these. What we'll actually find when we calculate out this H plus is that it's the same. 3.6 times 10 to the minus 5. It is the ratio of your weak acid and weak base that adjusts how much your H plus is going to need. If you think back to our equilibrium, if you increase the right and the left, they cancel out. By halving or doubling both sides of the reaction, there's no change in the equilibrium position. And so our H plus stays the same. And so this is still pH equals 4.44. In fact, as long as your weak acid-base mixture has a concentration greater than like 10 to the minus 6, this will be true. No matter how little or how much you have of it within reason, it will maintain that exact same pH. If there's any weak acid and base mixture in there, it will reach equilibrium. Just remember how little H plus is naturally in water. Pure water has a pH, has an H plus concentration of 1 times 10 to the minus 7. So we're still 360 times more than that in our dilute solution up here. The amount of H plus is dominated by the chemical, not by natural water. And so as long as your concentrations of your acid and base are reasonably large, they will always be exactly the same pH if they're the same ratio. Alright, we'll go ahead and pause there for this video. This was using acid and bases, calculating out pHs.